Good morning and welcome to your video tutorial to go along with your week 6 review. Please note that this review is due in the Dropbox by Wednesday midnight of next week. That is the 1st of October. On this video, this is the same Word document that I've given to you. I have changed the spacing, and you probably should also. I copied this from a PowerPoint onto the Word document, so some of the wording, like in the first one, says use the VT graph to the left. Well, actually it's below. So I think if you arrange the graphs the way I have on your paper, then it'll be easier to do this. So first we're going to start off with the very first thing we did in the year, which was transposing velocity graphs into acceleration time graphs. And if you remember, DEVA tells us that to get from a displacement time graph to velocity, I take the slope, and to get from a velocity time graph to acceleration, I take the slope. However, we go up the right side, down the left side, up the right side. If I'm in acceleration, I take the area, and if I want velocity, if I'm on velocity and want displacement, I take the area. So in this first question, we are on a velocity time graph, and we want acceleration, so that means we have to go down the left side using slope. So for each one of these sections, we need to take the slope. So if you set up your graph so that it's exactly right underneath, your acceleration time graph is exactly underneath your velocity time graph, so that you have the same time spacings aligned, it makes it much easier. If you notice right away, we have a positive slope here, a positive slope here. Both of these are positives. And this slope here is a negative. So that means we should expect to have some lines above 0 and then some lines below 0. So I'm going to put my line here. That's for 0 acceleration. So I have time on the x, and along here I have acceleration. The first slope goes from 0 to 2 seconds, and it is the rise over run, which is 6 divided by 2, which means that our slope is 3. So going 1, 2, 3 up here, I should have a straight line that represents an acceleration of 3 meters per second squared over 2 seconds. At that point in time, you notice on our velocity time graph we have a straight level line, which does not mean the object stopped, it just means it stopped accelerating. So we still have velocity, but we don't have acceleration. So our acceleration graph is going to go down to the bottom here, and we're going to have a straight line at 0. Then we have another positive acceleration. The rise over run here, rise here, run here. The rise goes from 6 to 10, which is 4, and the run goes from 4 to 6, which is 2. So that's 4 divided by 2 is 2. So that means for the next 2 seconds, I go up here to 2 and draw a line. And again, our velocity time graph levels out. So these lines up here represent 0 slope, which is 0 acceleration. So that means our line's going to go back down to the 0 line for no acceleration. And then we get a negative slope. Again, we're going to take rise over run. So here's our rise. Here's our run. But notice in this one, the rise is 0 minus 10. 0 minus 10 makes a negative 10, and that's where our negative slope comes in. And between 8 and 12 is 4. So we're taking a negative 10 divided by 4, which is a negative 2.5. So now our acceleration has to go down. So it's going to go down 1, 2.5, and over in the middle. Okay? So this is each one of these box-like shapes represent where the acceleration is. And remember, if you have constant acceleration, which we do in each one of these cases, and if you're asking yourself, well, how does she know that? It's because each one of these lines are a straight line. If this was not constant acceleration, this line here would have been a curve. But it is constant acceleration, so therefore it's going to be a level line on the acceleration graph. The acceleration does not change over that 2-second time period. So we get this very boxy looking acceleration. And you can expect that on the test. That's exactly what's going to happen on the test. Your velocity, you're going to be asked to do the same type of thing, and your velocity time graph will be transposed into a very boxy-like looking acceleration graph. The second question asks, what was the displacement of the object between 0 and 4 seconds? So we're on a velocity time graph. They want us to get displacement. So I have to go up, and I go up the right side by taking the area. So I need the area on the velocity time graph of this space right here, and I will have to divide it up into this triangle here, and then this rectangle here. So if I get the area of those two places, it will give me the displacement between 0 and 4 seconds. So I'm going to put displacement will equal the area of the triangle in the first place, which is going to be it's going to be 6 times 2, right? The base times the height divided by 2, plus the box, which is 2 across and 6 up, so that's 6 times 2. The answer will be 12 divided by 2, which is 6, plus 12, which equals 18. Very, very simple math. Okay. The key to this is knowing this DIVA acronym, or a little memory aid, if you will. Next, what is the acceleration at 4 seconds? Again, this is using your DIVA acronym. We go down the left side with slope. We go up the right side with area. So we are on a velocity time graph. That's right here in the middle. And they ask for acceleration. That means that we are going to have to take the slope at that particular point in time over that period to get the acceleration. So you want to take 2 points that actually fall in the intersection to get the most accurate answer. So 4 seconds is right here. So we have 1 point that is x equal to, x equal to 4, y equal to 0, and then we have another point up here at 0.8. So the rise over the run, and you should draw this out on your notebook paper when you are doing this so you don't get confused. Here's the rise, which is a negative 0.8. Notice it is a negative 0.8. And the run is 4. So that means that our acceleration is going to equal to negative 0.8 divided by 4. And it's going to be a negative acceleration, which we would expect looking at that slope. And that's just equal to a negative 0.2 meters per second squared. Now, some of you are probably thought at first, well, that 4 seconds is right on the 0 line. Isn't the acceleration 4? No, it is not. The velocity at exactly 4 seconds is 0, but the acceleration has to be the slope of the line. So don't get confused about that. At 4 seconds, the velocity is 0, but the acceleration is not. The object is still moving according to this graph. So the acceleration runs right through there. What it did do was it changed direction. So we have started talking about projectile motion. So if this was projectile motion, this point right here would be the top of the trajectory. Alrighty, so it's something that is changing direction at that point, and for just a very small instant it is 0 velocity, but it is still moving, so the acceleration is still there. Okay. Alrighty, next question. What is the speed of the object at 2 seconds? So speed in graph world is the same as velocity. Again, we are on an acceleration graph. They want velocity, so that means we have to take the area at 2 seconds. So I will draw a line here. That means I want this area in here. That's a triangle. So that means our velocity will equal 1/2 the base times the height. The base is 2, the height is 2. That's 2 times 2 divided by 2, which equals 2 meters per second. Very easy math. You just got to make sure you understand that DEVA concept. Okay, so here starts one that's a little bit more difficult. Using the equation, and there we have our quadratic equation involving distance, velocity, time, and acceleration. Use that equation to show that if two objects starting from rest have the following motion, object 1 falls freely for 3 seconds and object 2 falls freely for 9 seconds. Then compared to object 1, object 2 falls 9 times faster. So remember, draw yourself a picture. We have one object falling for 3 seconds. We have another object falling for 9 seconds. And the question is asking you about how far it falls. Object falls 9 times further. So that means we are talking about the distance that it falls, which means the distance is equal to the final distance minus the initial position. I should call x position because x alone is not distance. X minus x0 is the distance. So in other words, if it started at 0, there was some number x that it fell to, and that's what it's talking about. So our distance is going to equal x minus x0. Let's take a look at this equation then. To get x minus x0, I have to subtract x0 from both sides. And that would give us x minus x0 equals v0 times t plus 1/2. I'm going to erase this here. At squared. So now I have the equation in the form that it will tell me what the distance is for each of those objects if I have the proper numbers. So let's read the rest of the problem. Object 1 falls freely for 3 seconds. Object 2 falls freely for 9 seconds. So what that's telling me is I know that 9 is 3 times larger than 3. 3 times 3 equals 9. So that means that whatever distance the second object falls, its time is going to be 3 times greater. So let's look what happens to our equation when we put those concepts into it. Let's first take the object at 3 seconds. The object at 3 seconds, we know our initial velocity is 0 in free fall. The time is 3 plus 1/2, 9.8 times 3 squared. That means this part cancels out, and we get this equal to 4.9. That I got just by multiplying 0.5 times 9.8, taking 1/2 of 9.8 times 3 squared. That will give us the distance that the 3-second object fell. Now, we have to ask ourselves, what is different about the object falling for 9 seconds? The only thing different about it is the time that it was falling. 9.8 is the same. The acceleration will be the same. The initial velocity will be the same. It'll be 0. The only thing that will be different is this factor right here. So for the 9-second one, instead of having 4.9 times 3 squared, we would have 4.9 times 9 squared. But I'm going to write that a little bit differently. Okay, so for the 9-second, I'm going to make sure the 9-second object, this distance will equal 4.9, and instead of writing 9 in here, I'm going to write it as 3 times 3 squared. If you see that, then the only difference between this equation here and this equation here is that I have an extra 3 squared in it. I can write this as 4.9 times 3 squared times 3 squared. That means the difference between this and this is this 3 squared number right here. And 3 squared is 9. So that's our proof that it'll go 9 times further than the object that went 3 seconds. We will go over that in class, but it'll be easier on you if you go through that yourself a little bit before we talk about it. Okay, so the next one, an arrow leaves a bow with a speed of 42 meters per second. Its velocity is reduced to 34 meters per second by the time it hits the target. How much distance did the arrow travel over if it were in the air for 2.4 seconds? So again, the first thing we do is draw ourselves a little picture. Here's the beginning where the arrow starts, and here's the end where it hits the target. It leaves the bow with a speed of 42 meters per second. So for our givens, we have at the beginning our initial velocity is equal to 42 meters per second. Its velocity is reduced to 34 meters per second. So its final velocity is equal to 34 meters per second by the time it hits the target. How much distance did the arrow travel if it were in the air for 2.4 seconds? So we know that our time is equal to 2.4 seconds. And we know that the unknown, what we're looking for, is the distance. And remember that the distance is always equal to the final x minus the initial x. So that's what we're looking for. So now we need an equation, and notice we don't have acceleration in this. There is no acceleration given to us. We're not, the arrow is not, does not have any downward motion. We are to assume that it goes straight level. So there is no acceleration besides the fact that we know that it slowed down from 42 to 34. And so in this equation, in this problem, we are going to have to do it in 2 steps, because all of our distance equations have to have acceleration in it. So you have 2 equations that you could use for distance. The one that, well, let's just go ahead and figure out the acceleration first. Our acceleration here is going to be average acceleration. And so we're going to say that our average acceleration is equal to 34, our final, minus our initial velocity, divided by our time. And let me get that number for you. Okay, so that number is a negative 3.3. I'm going to round it off to 2 significant figures, and that's in meters per second squared. Okay, so now we have initial velocity, final velocity, time, acceleration, and we are looking for our x minus x0. At this point in time, our time factor we've used, and we do not need to use it in the equation that we actually are going to use here. So this is our final velocity squared is equal to our initial velocity squared plus 2 times the acceleration x times x minus x0. And of course, this is what we're looking for right here. This is our distance. So, substituting in, we would get that 34, this goes to 34 squared, is equal to the initial velocity squared, which is 42 squared, plus 2 times the acceleration, which is negative 3.3, times our distance d. Okay, I will leave that to your fine algebra skills to get the answer to that. In class, I'll go over that. I don't have quite enough room here to do that, so that is just now just an algebra problem. You're going to subtract 42 squared from each side, and then you're going to divide each side by 2 times negative 3.3. Okay, what is the acceleration of any object after it falls off another moving object? What you have to realize here is that the only reason why an object accelerates is because something is either pushing it or pulling it. There is a force applied on that object. So immediately after anything falls off of a moving object, it ceases to have acceleration anymore, because there now is no more is there an object pushing or pulling it. So in other words, if I have an airplane, here is my little airplane here. All right. And an object falls off of it. If this airplane was accelerating, the object that falls off of it will have no more acceleration because the plane is not pushing it anymore. However, the same is not, so the answer to number 7 is 0. What is the acceleration is equal to 0 after falling off. However, the same is not true about velocity. Velocity is a function, you might say, of the inertia. Remember inertia, remember this from middle school. Inertia says that everything, any object that is moving has motion, stays in motion. Any object that is still will stay still unless acted upon by an outside force. So anything that is dropped from this plane, it will have the same velocity as the plane was going at that point in time. So if this plane is going, let's say, 200 miles per hour, then any object that drops from it is also going 200 miles per hour and in the same direction as the plane is going. An example of this is, if you remember a few years back when the space shuttle fell apart, they could track the pieces of it by knowing the velocity of the space shuttle at the point in time that the pieces fell off of it. So each one of those pieces had the same velocity as the space shuttle did at that point in time. And by tracking that velocity across the Earth's surface, they could have a better idea of where to look for the wreckage. No math involved in that one. It's just understanding that concept in both of those. Okay, so the next one, an object falls from rest and hits the ground with a velocity of 50 meters per second. How far did it fall? At first this seems like an impossible problem because the only number they give you is a velocity of 50 meters per second. So again, let's draw a picture. Object falls. Here's our beginning. Here's our end. Okay? And for our givens, anytime an object falls from rest, we know that its initial velocity was equal to 0. We know that its initial position was 0. We can set it equal to that. And we know that the acceleration is equal to 9.8 meters per second squared because it's falling in the Earth's surface, in the Earth's gravitational field. So none of that was given to us, but that is what you are supposed to infer from the object just by the fact that it says the object falls from rest. That's how I got all three of those numbers. The one piece of information they do give us is that down here their final velocity is equal to 50 meters per second. So the unknown is how far did it fall? So how far is a distance, and we know that our distance is equal to our final position minus our initial position, which is equal to, that's what our unknown is. So that means we have to have an equation that has acceleration. It would like to have final velocity, initial velocity, and it has to have some kind of distance in it, x 0x. And the equation that fits that bill is our third one that says velocity squared, the final velocity squared equals the initial velocity squared plus 2 times the acceleration times x minus x0. And this, of course, is our distance. Substituting in, that says that 50 squared is equal to 0 plus 2 times 9.8 times our distance. So we're going to square 50 and then we're going to divide by 2 times 9.8 to get the answer. Now, let's say you didn't use this equation. Let's say you decided to use, the equation that said V final is equal to V initial plus AT. What you would have done after you decided that that was the equation is check off what you have and what you don't have. V final, yes, you have that. That's here. V initial, yes, you have that. That's here. Acceleration, yes, you have that. It's here. Okay? But then you would come to a point, time, wait a minute, I don't have time, and I don't have distance, so therefore this is not my equation. If you tried the second, the quadratic equation, if you tried this one, you would get x equals x0 plus the initial velocity times t plus 1/2 AT squared. Well, you're looking for x, so that's good. You have x0. You have v0. But again, you don't have time. So you know that this equation, again, would not be the one you wanted. And the only one left would be the third one. I'm going to end this video on this problem because this last two have to do more with projectile motion, which we are going to be talking about on Monday. And I will make a separate video for these last two problems.